Yes, so good afternoon, everyone, and thanks for the participation. My name is Yu. I'm from the ECE Department of Routers. And today, I'm very glad to be here to present my master's thesis. The topic is harnessing adversarial samples against voice assistants, and it's supervised by Professor Ying Chen. So the outline of my presentation will contain 5 parts. First, I will give a brief introduction of the background of the voice assistant and the speech recognition, and then I will explain my attack approach the system in detail. And I will also provide with evaluation and the future works on my research. And finally, I will give a total conclusion. So voice assistance is a system which can hear humans' commands and help assist with various kinds of works. They can help to play music, turn on the lights, or navigate to your home. And many commercial products are using voice assistants like Amazon Echo and Apple Siri and Google Assistant. They can help you bring your smart home and answer your questions. You can do various of things without even lift a finger. So voice assistants are widely used in recent societies. A survey conducted in the 2017 shows that nearly half of the Americans are using digital voice assistants like on their smartphones, like Apple Siri or Google Assistant. And then nearly half of it shows that for the next few years, there will be 50% more of people using the smart speakers. And this will lead to about a quarter of adults in America will begin to use smart speakers in the next 2 years. So the voice assistant contains of 3 processes: voice capture, speech recognition, and command execution. So as the voice assistant are bringing convenience to our daily life, so will there be security concerns in the convenience and the success behind it? So what if on the speech recognition part, it cannot recognize the command correctly? Like when Professor Richard wants to navigate to the home, but he navigates to the school. Or I said to turn on the light, but instead it triggers the fire alarm. So this will bring in security concerns, and we have to have a research on it. So first, let's give a background of the speech recognition. In a traditional procedure of speech recognition, it contains 3 parts: feature extraction, acoustic model, and the language model. In the feature extraction part, we will pre-processing the audio input and extract the FCC or PLP features of the raw audio. And for the acoustic model part, we will generate acoustic features like phonemes, which is the smallest unit of composing a word. And in the language model, we will kind of like of the grammar, define how words can be connected with each other. Like mouse and mouse, they here similar. But if I add a 12 before the word, it will have a likely probability of recognized as mouse or not mouse. So in our attack approach, the acoustic model is based on the deep neural network, and we aim to attack this part of the speech recognition. So before I will explain the attack approach in details, let's first give a brief introduction of the hidden Markov model. It's the central component of a modern speech recognition system. Each phoneme in the system has a unique HMM model, and it's a model which contains several states, and each state has a transfer probability between each other. Like in this model, in the state 0, it has a 60% of self-loop, and have a 40% of moving to the stage 1. A couple of states, a series conditions between certain states can define a phoneme. So, also, the deep neural network have already proved have written. They are vulnerable to carefully designed perturbations designed by adversarial samples. as we can see from this example, it's a sample based on image recognition. By adding a small perturbation to the photo of the panda, the DNN will recognize it as a gibbon, and he thinks it is 99% right. But we can see that the difference is impossible to be noticed by using eyes. The two pictures, if you use eyes, they're exactly the same as a panda, but for the deep neural network, it will recognize it as a gibbon. So we want to do the similar things from the audio input. So for our attack, I want to develop a sample on the audio input. Like for the humans, they will hear it as an ordinary music, like a popular song or a pure music. But for the DNN system, it will recognize it as a malicious command. Like for music, for the human, it's just a beautiful music. But for the iPhone, Siri, it will recognize it as, "Hey Siri, unlock the phone." So the aim of our work is first to make sure our attack can successfully fool the speech recognition system. And the system we aim to attack is Kaldi, which I will explain in details later. And we want to make the sample differ little with the original sound, making it unnoticeable for humans to hear the difference between it and be suspicious. So there are also some existing related works on this topic, but most attacks are against the system named deep speech. Deep speech is also an ASR system which is developed by Baidu in China, and it applies an end-to-end deep learning technique. It contains the audio as the input and directly gets the text from the DNN network. It skips the phonemes, the hidden Markov models, and makes the training part much easier and simpler. But attack against deep speech is much more easier, since first of all, it skips many useful steps. Although this makes the training part and makes it more easy to understand, this will bring more security concerns, and it is implemented by TensorFlow, which is so popular in the deep learning community, and this enables for the attack against it much more easier. And the other focused on the acoustic model based on GMM, which for the most of the ASR system now, the model is all based on DNN, not GMM. So their attacks all proved powerless against the model systems. And also some of the attacks require expensive and specific equipment, like using ultrasonic to embed the command in it, and this will cost too much, and their effects are not very good. By the day we began our study, only one of the existing studies aims to attack Kaldi, and by the day we finished, only two of the existing attacks aims to attack Kaldi, and one of them focused on making the perturbation unnoticeable to humans, not mainly based on how to attack it. So first, I will give a brief introduction of Kaldi. It's an open source toolkit used for speech recognition based on DNN and HMM. It has an overall better performance to all of the open source toolkits recently. For example, compared with deep speech, Kaldi has an error rate of 4%, while deep speech have an overall error rate of 6%. And also, it is the most popular toolkit in the research community. From the Google citations and the stars on the GitHub, we can see it is far much than other toolkits. So few attacks focusing on attacking Kaldi, and I test all other existing attacks. I use Kaldi to recognize them, and none of them can be decoded as the malicious command. All of the existing attacks are all proved powerless and harmless against Kaldi. So for our work, I choose this toolkit as our target attack. So we will describe the HMM topology in Kaldi in details. As we discussed before, for each phoneme, there contains a specific HM model. And for each phoneme in Kaldi, it has 3 HM states. And at the state 0, it has 50% to move to stage 2, or just move to stage 1. And at stage 1, it has the 50% of moving to stage 2 and 50% of self-loop. After we use Kaldi to process the audio input, it will give a sequence of transitions between certain states. And from the transition of each state, we can define a phoneme. So there is a transition model built in Kaldi. For the acoustic model, there is a pre-trained probability density function, PDF, and it will calculate the probability of all HMM states at each frame. The PDF is indexed using the PDF ID, and the output of the acoustic model contains the probability of each PDF ID at each frame. And we take this output to the language model, and a transition ID is used to index a specific transition between 2 HM states of the same phoneme, and the sequence of the specific transitions will determine which phoneme should be the final decoding result. So from the acoustic model, we get the probability of each frame, and from the language model, we will get the final decoding result. So let's see, here is a table to make these relationships more easy to understand. For each phoneme at each HM state, there is the PDF ID corresponding to it. And as we can see, for each transition, there is a unique transition ID to it. After the acoustic model, it will get the PDF ID at the probability of each PDF ID at each frame. And for the final result, we can get a sequence of transition ID, which we can see as an example of decoding the word no. It's composed of 2 phonemes. And we can see for the final decoding result, there's a sequence of transition IDs which we can make sure it's the phoneme of N and the phoneme of O. And from the transition ID, we can get the corresponding PDF ID. Although from the acoustic model, we can only get the probability, but from the final result, we can get a certain sequence that can lead to this decoding result. So as we can see, from this is a transition ID, and it corresponds to a unique PDF ID. So our attack approach is, first we get the PDF ID sequence of the malicious command, and also we get the original sound's PDF ID sequence. And by using a genetic algorithm, we craft the original sound, and we want it to the PDF ID generated by it is equal or close to the sequence of the malicious command. So if they have the same or close sequence, then the original sound can be decoded as the malicious command, not its original lyrics. So this is the overall attack approach of our study. For the original sound, we get the matrix which contains the probability of PDF ID sequence. And from the target command, we will derive the certain sequence that must lead it to the final result. So we want to minimize the distance between 2 sequences. But as I studied further into the Kaldi, into the transition model, I found there are several transition IDs which are different, but they share the same function. They share the same phoneme, the same state of HMM, and the same transition. So I have a thought: can we replace the transition IDs by the different IDs with the same function? Like from the result I showed before, the ID is 39705, but 39707, they are the same. They share the same states, but they have a different PDF ID. So I have a thought: can we replace the transition IDs with all its, you can see, the brothers which have the same functions. And so we can derive thousands of different PDF ID sequences as our target. So our target from 1 become to thousands of the same sequence, thousands of different sequences, but all can lead to the same result. So that's for the part of the derivation of the command. Also, we need to get the sequence of the original song. As I mentioned before, the output of the acoustic model is a matrix which contains the probability of each PDF ID at each frame. So we can extract the PDF ID which has the highest probability at each frame. Then that's the most likely sequence of the PDF ID. So, and if the most likely PDF ID sequence of the original song is close or equal to one of the PDF ID sequence of the command, then the song can be successfully recognized as the malicious command. So this is our attack approach. So how to craft the original song to make it decoded as the malicious command? We introduce a gradient independent algorithm, genetic algorithm. It's used for solving optimization problems that are based on the principle of natural selection. Like in association needs to evolve to fit the environment. Like the bird needs to fly in the sky, so they evolve their wings. And the fish needs to live in the water, so they don't have feet or hands, but they use fins to breathe. So we want to accept the same principle in crafted the song. For each generation, we only kept the song which have a likely probability of being decoded as the command. The algorithm is commonly used to generate high-quality samples by relying on bio-inspired operators such as mutation, crossover, and selection. And we add random noise to the original song to generate the adversarial sample. So for each generation, it calculates the score for each individual, and each individual is a crafted song, and the generation is a collection of them. Then based on crossover and mutation, it generates the next generation. It only keeps the one who has the best performance and eliminates all of the others. So we keep the iteration until we reach the maximum time of iteration, or we get the desired result. So for the initialization, it's quite simple. We use a third Python library Skype to convert the song into an array, and we randomly generate a noise to it. We want to make sure the noise can't make the original song differs too much from it. So we rule that for each noise, it must be in the 10 times of the elements in the original array. And by adding them together, we can get the correct song, and we can restore it to an audio file. So for the initialization part, we do this 20 times. So there are 20 individuals in one generation. And for scoring, scoring is what we decide which individual have an overall better performance. We calculate the distance of each most likely PDF ID sequence to all PDF ID sequences of the command, and we find the minimal distance of the crafted song. Since the shorter the distance is, the more likely it can be decoded as the command. So we set it to the -i as its score. So this because the higher the score is, the better performance the sample have. So this is part for the scoring. And crossover is a step to generate children for the next generation. We choose two individuals as the parents, and from these parents, we generate a child as the next generation. The probability of each individual we chosen is calculated using the softmax function. The higher performance an individual has, the higher probability it will be chosen as the parents to generate the next generation. So the function, the softmax function is shown in the slides. it is the most reasonable scoring function I found in our research, because the scores may differ a lot from each other. So we use it to make them don't differ too much from each other, but at the meanwhile contains the probability of it. The crossover is like the cross chromosome in biology. From the two parents, we let the child carry the two characteristics of both of the parents. We cut the array randomly. We cut into pieces, and for each piece, it will multiples a random float between 0 and 1 p. At the beginning, we set p to the 0.5, so we want the child to carry half of the characteristics from both of the parents. But in the later experiments, we found that we set p to a random value will highly increase the performance. So for each piece, there will be a random float p between 0 and 1. And for the child, it will contain the attributes for both of the parents. So this is the way we generate the child of the next generation.
How many bit float?
One float for each piece.
No, how many bit? What resolution float?
32.
32 bits.
Yes, 32. And also we need to do the mutation. Mutation is to add a relatively loud noise after the crossover up to the child. The probability of the mutation is defined by a variable mutation p. And if the best score of the generation doesn't increase compared to the generation before, we will increase the probability of the mutation. If the best score increases, we will set the mutation p to its original value. In our attack, we set the probability of mutation to 0.05. And if after one iteration the performance doesn't increase, we will increase it half of the times, and the maximum of the probability is 0.5. If without mutation, after many times of iterations, all the individuals will tend to become exactly the same, and will never will have a better performance. So this is the critical and the very essential part of the algorithm. Without mutation, after about hundreds of iterations, all the individuals in a generation will become exactly the same. So we use 3 audio clips as the original sum, and we evaluate the overall performance. We set the target commands be a simple word like yes, no, or open. The audio type is pure music, pop music, and just a voice command generated using the text-to-speech engine. And we set the maximum time of iteration to 2000 or 3000. As we can see, if we, despite the voice command, just use the pure music or pop music as the original sum, it can get an overall performance of 70%. And the pure music has the highest probability of success among all 3 audio types. This is because for the pure music and the pop music, even humans sometimes can't hear the lyrics in a song correctly, and the PDF probabilities in the matrix is low. It is like all the probabilities for each PDF ID are kindly the same, so it's easy to let the sequence for the command is higher than the others. But if we generate a pure voice command by the text-to-speech engine, the correct sequence of the probability function is much higher than the others. So it makes it really hard to embed the commands into it to make the sequence of we wanted be more convincing. So this results the success rate of the voice command be really low. Only one sample success of 10 experiments. So for current, I ran the code on the Google Cloud Compute Engine, because for iteration of thousands of times, it will contain about nearly 20 hours to do the total integration. Because for the scoring part, for each scoring part, I need to use Kaldi to do the decoding. Although Kaldi has a better performance, its speed is compared with other toolkits, its speed is low. So it will cause this results to the consumption of time. But for the similarity, the result is pretty good. For each song, the crafted song of the original song, they can have an overall similarity of over 97%. This will make the crafted song hard to be noticed by human. For human, they can be sound exactly the same.
Do you have any reason to believe that this correlation coefficient corresponds to what trained observers would report?
Because we can convert the audios to the arrays. So we first calculate the covariance between the two arrays, and we use the PCC to calculate the overall similarity among them.
Right, but what I was asking is correlation, the covariance is a mathematical similarity,
Yes.
right? Your ear is wildly nonlinear. So is there a reason to believe that that's a good representation for what people would hear?
Yes, I will show the result in the next slide.
Also, is it amplitude dependent? Loudness dependent? I mean, your ear is also very nonlinear in intensity.
No, with that.
So is the 99.08 the same for if it's played soft or it's played loud? Or do you have some standard level?
No, because the audio array also contains the information of the volume. So
okay.
Yes, if you for the same audio array, if you multiply all of the variables in it by 2 times, then the volume of the audio will also increase 2 times. So this increases the volume information in the array.
But the noise masking isn't going to be the same necessarily at 2 different volumes, loud and soft.
Yes.
Because your ear hears the loudness non-linearly. You know, the noise and the actual signal may not be both received the same way.
Okay, I will.
Right. So do you have a standard intensity level you use? Overall volume.
It's just generate the.
Use earphones or?
No, it's just the initial value of the sound generated of the text-to-speech engine. It's the initial value of it.
Right, but that's the generating loudness.
Yeah.
What you hear depends upon the room and where you're sitting and so on. I just wondered if you.
Yeah, it's
So I don't think you get a chance to study that part, right?
Yes.
So I think it's very good input. We should.
That's just
Yeah,
or
study
at least
that.
indicate what
Yeah,
the
indicate,
loudness
yeah,
is.
how the loudness plays a
It's-
factor here.
It's
If
for
any-
the audio separated through the air. And,
Right. The reason I say that is audio is measured in dB,
yes.
but you're adding the signals
Oh.
in intensity,
Okay.
and that's not a dB process. So it's very different to add 2 signals at a high level and at a low level.
Yeah, this is in the future work
Okay.
for the attack over the air. So we can hear some samples. This is the original song.
I think probably in your thesis, after this you still have some time, a few days. I think you can still do some loudness study. I think it would be good to include that.
Or at least say what it
some
is.
discussion, yeah, in the thesis, because when people read it, they will have questions.
Sure.
Also, I have a personal deep objection to people putting down 4 significant figures on a project where you haven't taken enough data to have 4 significant figures. 99.08 implies that you know that it's not 99.07. No, on the previous curve, you said 99.08, right? But you don't have enough samples to know 1 in
Right.
10,000 accuracy.
So
you should
your
round the
accuracy is
numbers,
not,
yeah.
round down your numbers,
Oh,
basically.
yeah.
Yeah, you don't have to put, as Rich said, the data is not sufficient or significant enough to back you up to the .08, right?
Actually, it is because the array is contains thousands of the variables in it. So the array is pretty long. It's
If you did the problem twice,
Yeah, well, you get.
right? Do you get the same answer to 1 part in 10 to the 4? I would be very surprised, and it would be a wonderful thing to add to your thesis. In other words, one of the things on the learning that would be interesting to know is if you run the same process twice and you have random probabilities for that, the splitting function, for example, right? That's random. So if you run it twice, do you get the same answer?
Yes, because this is calculated by a formula, so this will always get the same
No,
answer.
but not if the p times 1 minus p is random. If the crossovers are random.
No, we calculate the similarity of the correct cell. This part doesn't contain the crossover. It's already finished by the genetic algorithm. We just compare the similarity between the two audio inputs.
I understand.
Yeah.
Yeah, okay. But to get to the audio output,
Yes.
you had to do the genetic algorithm.
Yes.
Genetic algorithm has random numbers in it,
Yes.
right? If you do the genetic algorithm twice,
This is
do you get the same answer?
based on 10 times of the overall.
Okay.
It's overall.
So you do the genetic algorithm 10 times.
Yes, for each 10 times, and for this two 5 times. This is
Okay.
the absolute
And for
minimum.
each one of the 10 are accurate to 1 in 10,000? That's what that says. It says that I look at all 10 of those, I
Yes.
get the same result to 1 in 10, to 1 part in 10,000. Are
For
they equal to each other, all 10 of this? You do it 10 times
Yes.
with random numbers,
yes,
right? Is the result coming out, when you do the correlation or the covariance with the original sample, do you get the same number each time?
I don't think so. I really don't think the 2 digits after the decimal
Yeah.
point is that important.
But
Significantly-
there is a piece that is important. I would love to see how the genetic algorithm
Shape, yeah.
shapes up, because you said it's a 32-bit float.
yes,
So there is something like 10 to the 9 ways to do the crossover, right? And you have 10 to the 9 ways of doing the crossover. How does that, you sample a very small part of the space, right? There are many different genetic results from the genetic algorithm. It's a huge space. You're sampling only a very small piece of that space. And you have no gradient, as you talked about in the future work. You have no gradient to guide you. So you're just randomly sampling through that space,
yes.
right? And you're saying, I would like to know how flat that space is, how well it represents the problem. Does that make sense? Do you understand what I'm
Yeah,
saying? Right. It would be an interesting algorithm to say,
to look at that, right.
to look at the genetic algorithm and see, if you do it 10 times, boy, if they all come into the set, that says that almost any answer would work, which is a really interesting result.
Yeah, but I doubt that if you run, I don't think he's going to get the results that is, that you're going to get every result is concentrated to that.
Right, I
to
wouldn't
that
think so.
range. I don't think he can. I don't think his results could achieve that.
I
at this
wouldn't,
moment.
you're looking at achievement, I'm looking at, there's a research component to this which says, if I do it 10 times, what is the variance?
Yeah,
Right.
I think. we'd
And
like
that
to
tells
see
you how
that.
this scales to a bigger
Right,
problem,
Right,
right? If the variance is small, this will scale to a bigger problem and be more useful.
right, I agree.
There's some knowledge behind that might be
Right.
interesting to know. Okay,
Yeah,
thank you, I was
will.
just,
I will change this part because I used a formula to calculate the similarity. Maybe there's something wrong with the formula when I implement it.
No, we didn't say there's something wrong with the
No, no, no.
formula. No. I think Rich's point is that we like to see, okay, the distribution of your results, right? You can see the distribution of your results, and also you can calculate the mean and also the variance, right?
Yes.
So we can look at the variance and understand how wide or how narrow the variance could be.
Yeah, I only
in
calculate
this
the
case.
mean. I didn't calculate the variance.
Yeah, you can easily extend it to
Yeah, yeah,
calculate
sure,
the
sure, sure.
variance, right?
Yeah.
it's very unusual to use a genetic algorithm with only a few thousand iterations,
Yeah.
because the space you're searching is huge,
Yeah,
right? You have all the crossovers plus the random mutations.
Mhm.
The space is probably 10 to the 12 maybe more possible outcomes, and you tried 2,000 of them, or a few thousand of them.
Yes, because
And so it's really interesting to see what the shape of that space looks like.
yes, because to the time limitation, so
Of course. This is a master's, not a PhD, I understand.
I only use 2,000.
Okay.
Okay,
That's
thanks
good,
for this session. I will modify the thesis
Yeah,
later.
well, we can talk about it afterwards. I just wanted to know if you knew the answer to that. Thank you.
Okay, sure. So maybe we can listen to some samples.
Mhm.
We can see the waveforms are nearly the same, and here is the original sound, and here is the. Can you hear the difference between the?
Not at all.
Yes, but here is the difference. Here's the difference between the two sounds, and then this perturbation caused the result become exactly the difference.
Yes.
And here is the voice command. Yes.
Yes.
Can you hear the difference between?
It's right here.
And here is the difference. Yes, this perturbation makes the yes be recognized as the no. It is generated by a text-to-speech engine.
Yes.
So for the future work, since we are now using a gradient-independent genetic algorithm, we try to implement the gradient descent. We want to fully restore the acoustic model of Kaldi in the TensorFlow. After digging into the source code of the Kaldi, I extracted all the parameters of the deep neural network and all structures, the layers, and the layer's active function. I got all of the parameters of it. But it's huge. It's written in a text file. It's about 100 MB, so it be a huge task to fully restore it. It's used based on a time delay neural network, which is TDNN, and we can refer to each green node as the MFCC feature at each frame. And for the next layer of the node, it will accept 2 of the continuous time as the feature to the next layer. And for each node, it shares the same weight to the next layer. You can see from the color of the arrow, the same color means the same weight. So for each data at the same time, it will share the same weight to all of the layers layers in the next. So this makes it suitable for time series problems like speech recognition, because it's a series of commands, not they are depend to each other. And also we want to extend our work to speaker verification. Like the work I'm working on is like when I say, hey Google, take me to home, it will realize that trigger the fire alarm. But I want to do the future work as when I am saying, Professor Chen's smartphone will recognize that she is saying. So recognize my voice as other's voice. So this will raise another security concern. Because for Apple Siri, it can only be waked by the owner's voice, not others. So if we can extend our work to speaker verification, let my voice be recognized as the owner's voice, then I can do the hacking or any malicious things much more easier. And also we want to extend our attack over the air. We want to separate our sample through the air and can be recognized by the ASR system. For now, we only directly feed the sample to the recognition system. Because we generate our attack by adding small perturbations in it. But the noise in the air, they also have noise in the air, and they will largely influence the perturbations that we add to it. And then it will make the attack powerless. So we aim to build a random noise model and add it to the original sound before we implement the genetic algorithm. So this is for the future work. And for the conclusion, we demonstrate that voice assistant will bring in security concerns, and the attackers may embed commands in sounds that can fool voice assistants, but not detected by the human. We developed a gradient independent way to generate such attack, and we will use another way to improve it and then extend our work to speaker verification.
Could you clarify what you mean by over the air? Do you mean transmitted by radio, or do you mean by speaker?
By speaker.
By speaker. So when you actually launch it into the air,
Yes.
the ambient noise is enough to affect the attack,
Yes.
to remove coordination of the attack. Okay.
Yeah.
Yeah.
Yes.
Hmm.
So I want to show my special thanks to my supervisor, Professor Yin Chen, and my mentor Jian Liu and Chen Wang. Without their help, I can never finish this thesis. So, do you have any questions?